So today we're going to start chapter 5 on memory hierarchy, and the concepts that we're going to cover, they're really elegant. I really like this chapter. And of course it's not about the insides of the processor itself because as we have been covering, but we know that a processor without a memory infrastructure, without a storage infrastructure, cannot do much. It needs that infrastructure to store the program. It needs that infrastructure to store data. So they are closely coupled from a performance perspective, very symbiotic. So we're going to look at that relationship and then look at what are the techniques and the things that we can do to make sure that the memory infrastructure, the storage infrastructure, also supports the high performance techniques that we have been discussing on the processor side. So if you think about how all this fits together in a computing system, you're going to have a compiler that's going to generate the code, and the processor, which as we have discussed, has two distinct and very important parts: the data path that processes the data under the control of the program through a hardware controller. And that data and that program reside in memory. You need a global type of storage. So it's this memory hierarchy that we're going to be looking at. So here at a high level, we see that block, but we're going to see what that hierarchy looks like very holistically. When we're going to be referring to as memory, we're including the cache, different cache levels, the main memory, DRAM, and also the disk. So the disk is also viewed as memory as well. So those are the main pieces. Whether in these days the disk is not just a magnetic type of device, it can be also a solid state disk device. And then you have, of course, the devices, the input and output devices, whether it's networking, video, graphics, keyboard, mouse, and so forth. So that's the hierarchy. When we talk about cache, we're going to be referring to different levels. So you have to keep in mind that these days there can be 3 levels of cache with different types of organization, depending on how removed they are, the different levels from the processor itself. So remember that this is a hierarchy. It starts at the top. On the top is the memory that is closest to the processor. So the processor is at the top, and then you get this type of memory pyramid. And closest to the processor is the cache levels. Then the main memory, which is always the DRAM. And then below that is the disk in this hierarchy. And we're going to look at, most of the chapter is about caches and cache organization. A little bit about main memory, but there is not much that you can do about the main memory other than the interleaving techniques and different types of data rates that we're going to be discussing. But of the 3, that's the most straightforward. Then we're going to talk about virtual memory, which is a technique related to the disk or to the mass storage. Again, whether the disk is solid state or magnetic. And that we're going to spend some time on that, hopefully towards the end of the chapter. Hopefully we can get there. We're sort of running out of days here, but hopefully we can cover everything, and we're going to see the techniques that are similar to cache when it comes to virtual memory, and what are the parts of those techniques that are different than cache. So I think it's going to be, hopefully you'll find it very interesting. Now, if you look at sort of a first order budget for a computing environment, for say for a workstation, what you see is that 25% of that cost is going to go to Intel. It's going to go to the processor, and another 25% is going to go to the cost of the memory. So the main memory is going to be a big part of that, but the disk as well as and in this type of budget, the caches are not included because normally they are part of the chip or the chipset of the processor. So that's on the processor. But what you see here is that 50% of the cost is the processor and the memory, and then the other 50% is everything else. The box, the power supply, the different I/O, etc. So the memory is very important. It has a tangible effect on the cost. And when it comes to memory, what you want to have is lots of it, and you want it to be really fast. But we're going to see that because of the way memory is constructed, the way that it is designed, those two objectives conflict with each other. If you want fast memory, it's going to be expensive. And if you want lots of it, and fast, then it's going to be very, very expensive. So what we can do is come up with a techniques or a set of techniques and a way that we can create effectively the fact that you have fast memory and you have lots of it. And as you see, this doesn't come for free. So every time you get some type of improvement, there is something that you have to spend for it. And what you can hope is that when you do the analysis for the return on the investment of what you are putting in extra, that you are getting enough performance improvement. And what you have to spend in reality is redundancy. You have to duplicate memory. So you have to spend more memory and duplicate memory resources to create this illusion of lots of fast memory without a linear increase in the cost for the fast memory. And at the center of that technique are the concepts is the concept of locality. And there are two basic types, but the concept of locality. And we'll discuss how that locality manifests itself in software. And we are lucky that software naturally exhibits this characteristic of locality. If software didn't exhibit this characteristic of locality, then we could not employ these techniques. But we observed that software exhibits these characteristics, and we came up with these clever techniques that allow us to create this effect of fast memory, loss of fast memory, without the linear incremental cost for it. And what locality is, and one classic example that is used, if you can visualize, being in a library, and hopefully you all being in a library, and you have the tables, and then you have the stacks of books, and let's say that in this case you're actually using like real paper books to do some research and write a paper, and you're doing that at the table, and you look up a book that you need for for this paper, to help you write this paper. So you go to the stacks, retrieve the book and bring it to the table, and you look up the reference material that you needed to look up in the book. You use it as you're writing and typing your paper. But think about it, when you finish looking up the book, you don't close the book and return it to the stack. That's not what you do. You leave it on the table because you know that what you're doing, writing a paper on some subject, has the characteristic that if you looked up a reference in that book and that book is about the subject that you're writing about, there is a good chance that you're going to need the book again. So it's kind of common sense. You don't return the book immediately. You leave it on the table because you think that you're going to need it, or you think that the likelihood of you needing the book again is high. That is locality. The activity that you are doing, writing this paper, has an inherent and intrinsic characteristic of temporal locality. And that says that if you needed a resource now, it is likely that you are going to need the same resource soon. So you leave the book on the table. So that's one part of the locality. But let's say that the way that the books are organized on the stacks are that all the books about a particular subject are there together. And that's the way that books are organized in a library, right? So when you go and get this one book that you looked up, you look at the other books that are around there in the shelf and say, well, this book is about sort of the same thing. It's related. So I'm going to take this other couple of books so I don't have to come back to the stack. And I have those on the table. So instead of taking one book, now you're taking maybe 3 now to the table. And you use one and leave it there. And maybe later on you use another one and hey, you already have it there. You don't have to go to the stack. So that's locality as well. That's another type of locality. That's spatial locality because we refer to the fact that the books were especially collocated on the shelf. That is a classic analogy that we use to discuss locality as it relates to memory, because now let's translate that analogy to a memory hierarchy. The stacks are your main memory, your larger memory. The table is going to be your cache, where you just have a subset of what is on main memory, on the stacks. And what you take to the table is a block, or also known as a line of cache of words. So we're going to see it specifically, but hopefully this gives you a good appreciation for the concepts of locality that are rooted in common sense, but they're really clever, they're really elegant, and that observation is pretty cool. So now in programs, what are the inherent characteristics of programs? Is that programs access small portions of their address space at any time. So they have this temporal locality. Think about code. If you fetch some words or a word of code, the likelihood is great that you're going to need that word again. Think of a loop, for example. So the likelihood is large. So that's the temporal locality. And then think about the way that words and programs are constructed, that these are just lines of code one after the other. So if you use a word of code, well, the likelihood is high that you will need the next one, which is close by in memory. So that's a spatial locality. And on data, same thing. So if you retrieve something on the data space, think of a counting variable, so some index of a loop. You're going to keep using that data. And if you retrieve some data, maybe you need the data that is close by. Think of an array. So code and data, just like books in a library, exhibit this characteristic. And that's what we exploit to come up with these techniques, to come up with a cache system that allows us to effectively get high performance with lower cost of memory. The formal definition is what is in blue here. Okay? If an item is referenced, it will tend to be referenced again soon. So that is the definition of temporal locality, the formal definition. Okay? And then the formal definition of a spatial locality is if an item is referenced, items whose addresses are close by tend to be referenced soon. And when we say items, we can be talking about either code or data. All right. So how do we take advantage of that? And in the broadest sense, in this whole hierarchy, what we're going to see is that everything is stored on disk. If you look at your computer if you have a PC and you look at and it may be hidden, you may have to turn on the show hidden folders in the program that you use to look up the files. You're going to see a very large file, usually with extension .sys. SYS. This is the virtual memory file. So everything is stored on disk because your processor can address much more memory in its native address space that actually you would be willing to pay for in your laptop or in your PC. But how do we give, if we don't even have the semiconductor, the semiconductor memory to give it that much, how do we still give it to it? Well, we give it in form of the disk because the disk is very inexpensive and we do have the space there. So we're going to see that everything is stored on disk and then it goes up from there. A subset of the whole that is on the disk is going to be in main memory, in DRAM. But then a subset, yet another subset, smaller, of what is in DRAM is going to be in the cache or in the cache hierarchy. Again, when we go through the detailed examples, we're going to talk about a single level, but you have to be thinking that all of this can be translated to multi-levels with the same set of principles and organization. So in this slide, I wanted to talk about memory hierarchy and some basic facts. And again, the facts are that large memories are slow. So I mentioned that, for example, the disk, very large, very slow. It's an electromechanical system. And anytime that you have mechanics involved, you will have to deal with inertial and masses. So it's going to be naturally slow. And fast memories are small. So on the other end, on the electronic side, even memories that are all electronic, if you confine your discussion to the electronic memories, smaller memories are going to be faster. Why? Because you're going to have shorter connection lines, smaller transistors, smaller capacitances, and it's all about the RC delays. So smaller conduction lines, smaller resistance, smaller devices, and smaller conduction lines, smaller capacitances, smaller R's, smaller C's, smaller RC's, smaller delays. Okay. So then how do we look at this trade-off of technologies? Of, on the one hand, I have large memories, which I want, but it's slow. On the other end, I have fast memories, but they need to be small. And that's basically the fighting uh, of the requirements. And also, another dimension is that I want low cost. So large memories are slow and they're also inexpensive. Fast memories need to be small, but they are very expensive compared to the large ones. So we do it with hierarchy, and that's why this chapter is called Memory Hierarchy. We do it with parallelism. We have seen that applied to the actual organization of processors. And in the context of memory hierarchies, we're going to see that what allows us to do this effectively are the intrinsic characteristics of code to exhibit locality, both temporal locality and spatial locality. So I said that this was a hierarchy, a pyramid of memory technologies, and at the top was the processor. And you go down as you get logically and actually physically removed from the processor. So next to the processor is going to be, and in this case we're showing two levels of cache. Level 1 cache, so that's going to be the fastest storage and the smaller one. And it's the fastest because it's smaller. Then you're going to have level 2 cache, larger and slower. The technology used in level 1 and level 2 cache are the same type of circuit design. The only reason that one is slower than the other is because it's larger, exclusively. Then we have main memory, which is a different circuit design technology and technique than the caches. So this one is going to be slower because it's a different design technique. It's a different type of construction, physical construction, and also because it's larger. And then you have what we can call secondary memory. Let's just refer to that as the disk, which is going to be even larger, but even slower because the main reason is that it's electromechanical. So levels 1 and 2 of cache are the fastest. One is smaller and faster because it's smaller. And then we have main memory. That's DRAM, different type of construction. And then we have secondary memory, the disk, which is yet another type of construction. It's electromechanical in nature. So as you get removed from the processor, your access time increases. So when we talk about the speed of the memory, whether the memory is slower or faster, we are talking about the access time. How long does the processor need to wait for an item that it references to get back to it, to its register file, where it can do things with it? So, and the processor in this dichotomy is the fastest element, and it just goes slower from there. So here you can see another type of diagram. Let's say that here we have the processor, here we have the cache, and let's call this one the main memory. So this one is larger, and this one is smaller, and is next to the processor, and we know that this one is going to be much faster than this larger memory. So let's start introducing some terminology. We are going to talk about a block of cache or a line of cache, and that is the indivisible unit of items that we always keep together. We could define that block to be a single word, or we could define that block to be multiple words. Just like in the library analogy, I can define my package, what I bring from the shelf, from the stacks, as a single book, or I can define that package as 3 books. So I can say every time I go to the stack, I'm going to get the book that I want, but also I'm going to get the 2 books that are next to it. So that becomes the definition of what I always bring. That is the block. Now, I mentioned that when we put together this scheme, we don't get something for nothing. What we get is that we have to pay for redundancy. The redundancy comes in that whatever is at a higher level, present at a higher level, is always going to be at a lower level. We are not replacing anything, we are copying. So this block of cache here resides in main memory as well as it resides in cache. So now I have to duplicate the storage. So I'm really not gaining a storage. I'm actually have to spend more storage, and we'll see that it's not just copying the item. I have to actually have support items that I have to generate. So it actually costs me, but it's a lot less than having this block of this type of memory. If this is DRAM and this is cache. And I may never actually be able to, because if I made this type of block this size, it will degrade the speed. Anyways, I need it to be small. So I'm getting around that impossibility by introducing this type of redundancy. Another term that we want to introduce is a hit. A hit is when the processor finds what it wants, what it's looking for in this immediate block here in the cache. Notice that if this is smaller than this bottom block, the main memory, and everything that is at the upper block in the cache is also in the lower block in main memory, there is a many-to-one correspondence from blocks in the larger main memory to the cache. So we're going to see that multiple blocks here are going to map to the same storage here, because this one is smaller. And because of that, it may be that if the processor is looking for something, it may not be here in this copy. So that would be a miss. If it finds it, it's a hit. If it doesn't find it, it's a miss. Now, when something is not here, when I have a miss, I'm going to retrieve it from the lower level and put it in the upper level. Why? Because of locality. I say I'm needing it, so I'm going to take it from the stacks to the table, because I'm going to leave it there until something forces me to override it, because if I need it now, I'm going to need it again soon. Now, if this memory down here is lower than this one, and I don't have something, and I have a miss, and I have to retrieve it from the lower level and put it in the cache, it's going to take me longer, because this is a slower memory. The access time is longer. So we call that the miss penalty. If I have a miss, I have to bring it from main memory to the cache. It's going to take me longer. So in time, it's going to, I call that a miss penalty. Then the quality of these cache schemes are measuring what is called the miss ratio. How many misses do you have per accesses, for the number of accesses that you are affecting? So that's going to be a proportion and or a percentage. And of course, the hit ratio is 1 minus the miss ratio. And also, the miss ratio is 1 minus the hit ratio. And we always keep this block together. So the fact that we take something from the lower level to the upper level, from the main memory to the cache, there we are making use of the temporal locality. The fact that we have a block, and we not only bring, if the block is greater than one word, and we don't not only bring the block that we need, the item that we need, but the items that are nearby, spatially in memory, there we're taking advantage of the spatial locality. So these are just the same. Now, the one thing to highlight here is that the hit time, which is the time that it takes the processor to access an item that is in the cache, is much smaller than the miss penalty, because the miss penalty has to do with the access time to the lower memory. In the case of the block that is here, let's say that this is DRAM, the access time for DRAM is a lot longer than the type of cache memory that is SRAM, static RAM, versus dynamic RAM, which is the larger block here. So the miss penalty is going to be much larger or longer than the hit time. So obviously, we want to minimize the miss ratio so that we minimize the miss penalty, the aggregate, and that helps keep our performance high. One thing that you will see is that these systems are highly nonlinear, highly heterogeneous, so there are no equations here. Maybe other than some obvious arithmetic to compute the size given how you organize the blocks and things like that, but the behavior, there is no equation for the miss ratio, which is what you really want to minimize, which is tied to the performance via the aggregate of the miss penalty. These systems you have to simulate. And if you are a computer engineering student and you're going to go on and take lab 2, your first lab is going to be the simulation of a cache system where you're actually going to simulate the behavior of it as you actually run code traces through your simulator. So you have to build this simulator. So that's a very interesting exercise that we have there. Now let's digress a bit and talk about memory technology. And this data is exclusively to give you a relative appreciation of the different memory technologies in terms of sizes, in terms of speed, in terms of cost. It's very hard to keep it up to date because technology is advancing all the time. But what you want to get an appreciation for here is the relative, uh, how relative these parameters are. Again, time, cost, size, and how many orders of magnitude they are apart from each other. So if at some point, whenever this data was compiled, if we had a static RAM, which is what cache is made of, is the technology that we use, and we have access times in the half to 2.5 nanoseconds, you could have expected to pay about $2,000 to $5,000 per gigabyte when we took this snapshot. At the same time, DRAM, which is your main memory, so you're going to buy a computer at Best Buy and they tell you that you have 16 gig of memory, that's what they're talking about. Access time would be in the 50 to 70 nanoseconds, so well beyond an order of magnitude of the static RAM, but couple of order of magnitudes on cost. Could have expected to pay about $20 to $75 per gigabyte. And then, if you look at magnetic disks, the access time, which we're going to see what the components of that are, just for fun, you would see that they were in the 5 to 20 millisecond access time, but you would be looking at paying 20 cents to $2 per gigabyte. So now you're looking at, again, another couple of magnitudes below on the cost, but about 3 to 4 the magnitude higher on the delays or the access time. So again, what do we want? We want memory that is this cost, so we can have a lot of it, but is this fast. That's what we're going to try to do, and with the overall concept of memory hierarchy, starting with the cache, and you're going to see that we actually do it. We can do it. Not 100%, but if you are measuring miss ratios as a measure for how effective this is, as a measure of efficacy of the approach, you're going to see that normal miss ratios are well in the low single digits of percentage. 2%, 5%, and lower. So that means that your hit ratio is in the high 90s as a percentage. So that means that 90% of the time, or close, high 90s% of the time, you are actually servicing the processor for the items that it is referencing with the capacity that looks like this huge memory at a sustained speed that is the one of the memory that is closest to it, which is the cache. So this is great design, great technology, and great techniques. So again, cache uses SRAM, so we call that a static RAM, and you are familiar with the type of that type of memory. You have been using that in your designs. So you have an address and an output. You have these are read-write memory, so you have also data in. You have write enables. You can have an output enable signal. You can have a chip select that selects the specific chip, and you also have a clock. So these are synchronous devices, and the DRAM, it also uses the same type of interfaces. There used to be a time when DRAM was not necessarily clocked, was asynchronous, but these days everything is synchronous, so we call SDRAM. And the differences is in the bulk of the storage cells where you actually store the bits. So SRAM is made of the normal cell takes 6 transistors. 6 transistors. So hence it is fast, but it's high power, and it is on a cell by cell basis, on a bit by bit basis, is huge compared to DRAM actually, and that's why you cannot afford to have a lot of it, because it becomes very large, physically large, very quickly, and then the speed gets degraded very quickly, and the power goes up. So these are like storing bits in flip-flops. So as long as power is on, you can have your storage there forever. The DRAM is slower. It doesn't use transistors for storage. Actually, the one transistor that the 1-bit cell uses is used as a switch to access the storage element, which is actually a capacitor. So DRAM uses a capacitor to store a bit, the charge on the capacitor, and because of that, the charge in the capacitor leaks out, so it needs to be refreshed. Otherwise, you can lose, even with power applied, you can lose what you have stored in the DRAM if you don't refresh the charge. So how do you refresh it? Well, you figure out, given the technology and the sizes of the capacitors, how long is it going to take to degrade the charge, and you make sure that with some safety margins, time-wise, that you go and you refresh it regularly well before that charge degrades. So normally, DRAM needs to be refreshed about every 8 milliseconds, and this consumes about 1 to 2% of the actual activity of the DRAM. So it's a relatively low overhead, but the main thing is that it's slow. Construction-wise, that's just nice to know. It has and all memories actually are organized as rows and columns. Specifically, DRAM can have strobe lines instead of clocks, but this is more like the older DRAM. And the RAS and CAS lines stood for row axis strobe and column axis strobe. But all memories are basically a 2D array of bits. And then you have rows and columns, and from the address, you essentially can tell which column and in which row and which column your data is. So you have row decoders, and then you can have column muxes to get your data and so forth. But that has to do more with the actual circuit and physical design of DRAM. That's not what we're doing here. We just need to, I just want to give you enough information, but the point is that for us is a storage resource that have different characteristics when it comes to cost and how much you can have of it, and speed or access time. That's really the level of abstraction at which we look these memories. So again, SRAM versus DRAM, right? So SRAM faster, bigger, DRAM smaller, slower, different circuit design. It's just some of what I said before. Now, the whole CAS and RAS, as I said, that had to do with the older technology. Today's DRAM is really synchronous. So the SDRAM, where you basically have a clock and you got data on a particular edge of that clock. Then we have the double data rate type of DRAM, which we were able to access on both edges of the clock. And then the modern DRAM has two clocks in quadrature, which allows, and then you get data on both edges, so that allows you to get data effectively on a faster clock or at a faster rate. And that's kind of the state of the art of DRAM these days. But this is interesting. And again, it's hard to keep adding lines to the data, but what you're supposed to get is the trend. And if you start looking at normalized to the recent years and going back, what you would see is that back in the 80s, what you could get in terms of DRAM was about 64 kilobits. And if you look at the price per bit from today, on a gigabytes basis with the costs at that point, you would be paying about $1.5 million per gigabyte. And then you can see how it drops off and how the size goes up. So that ratio of bit per dollar goes up hugely, or the reciprocal of that, dollars per gigabit, goes down tremendously. So that allows, actually, this trend is what fueled the advances in multi-level caches, because now that we have the memory, we can have more, but also there is a similar trend on the SRAM side. And if you have that trend as well, and you take advantage of it, then you can come up with different levels of cache, where you can afford larger caches. And the only reason that you have multi-levels with smaller caches at the top is because if you make the SRAM bigger, it's going to get slower. There is nothing you can do about that, and that's just basically because of RC delays. That's the root of that phenomenon. So what are the performance factors of DRAMs? Well, we talked about synchronous. So if you have synchronous and do things on the edges, you can get improved bandwidth because you can burst the transfers. If you have buffering, you can you can read and also refresh in parallel because now you have a buffer. And again, if you can put more transistors and more devices like capacitors in a single chip, it allows you to do or apply these types of techniques that rely to a certain extent in redundancy. Another thing that you can do to improve bandwidth is banking and interleaving. So we're going to take a closer look at that one because these two refer to the actual architecture and construction and circuit design of the chip, inside the chip, but the banking and the interleaving has to do more of how we use the actual DRAM chips, how we use them on a board or in a module. So let's look at that. How do we increase memory bandwidth because DRAM is so slow? Let's say that we have this type of organization, and we have the processor here, and we have a bus to interface with the cache. So this is going to be, let's say, 1 word wide. We can deliver 1 word to the processor. And then here we have the cache, and then between the cache and the DRAM, we have a bus that is the same width, 1 word with the main memory, the DRAM. Now the problem there is going to be that this bus, because the memory here, the DRAM is much lower, the bus between the cache and the memory is going to run much lower than this bus. That is the main contributor of the miss penalty, because if you have a miss on the cache and you don't find it here, if the processor doesn't find it, now you have to come here and bring it into the cache through this bus, which is, it can be 15 times lower than this bus, because this bus is between processor and SRAM, but this bus is between SRAM and DRAM. So that's the miss penalty. Well, one thing you could do is, well, you could say, well, I'm going to organize this memory in a way that I'm going to have a very wide bus here, so that even though it takes longer, I'm getting more, so effectively, I'm getting a lot of data, and in here, I can have a multiplexer with a slower bus on this side, which is synchronized with this one and delivered to the processor. And that conceptually might work, but there is a real issue with actually making and synchronizing wide buses. Lots of wires that need to be synchronized. So that this has some drawbacks. But definitely is better than this, and you can improve the bandwidth a lot. Another approach that tries to be as good as this one without the problem of the physical design of wide buses is what is called banking or interleaving of memory. And what that is that instead of having this deep memory, I'm going to have multiple banks, actual multiple physical banks or chips or modules, but I'm going to keep this bus narrower, and also I'm going to run it at a higher speed because I'm going to be looking at sort of a round robin at the banks and collecting the items and feeding it to the cache at a higher rate. So this utilizes some of the concepts of pipelining. So even though the memory here is still slow, while this memory is accessing, I already addressed this one. So this one is accessing, and I address this one is accessing, and now I address this one is accessing. So by the time I get here, I go back and this one is ready. So I shoot it up. And now I can come back to this one and do the same thing. So essentially, it's pipelining in time the access of the memory. But for that, you have to have separate physical memory chips or banks. So that concept is called interleaving the memory organization. And I can get close to this with a narrow bus that doesn't have the physical issues that a wide bus has. This is the state of the art of memory organization. That's what we do. That's what's happening in your motherboard right now. So let's look at some examples for this. So let's say that we have one memory bus clock cycle for address transfer. And let's say that the DRAM access is 15 memory bus clock cycles. And here the reference is the bus cycle between the processor and the cache. And let's say that there is a bus clock cycle for the actual transfer. How would you calculate the miss penalty if you have a miss? So let's look at, you can have different cases, forward blocks and one word wide RAM. You could have a case of 4 words blocks and 2 word wide memory, or 4. So that would be basically as wide as you can get, because that's the width of your block. And then the other case would be with 4 banks for interleaved memory. So if I go back to the previous slide, the first case is where I have 4 words for the block. So every time there is a miss, I have to come here and get 4 blocks, but I can only get 1 word at a time because this is an error bus. Here are cases 2 and 3. I can have this be 2 words wide and then do 2 cycles and get 2 at a time. Or I can have this 4 wide and just have a single transfer of all 4 words for the block. The other one, the last case, case 4, is this case, where I'm using interleaving. I have 4 banks, 1 bank per word to get a block, but then I transfer via a faster narrow bus. So in essence, this would be the narrow memory organization. This 2 is for the wide bus, and this is for the interleaving. So here it is. So the miss penalty for, let's just pick 2 of the previous ones. So this would be the Y bus here, that is 4 words. We have that the miss penalty is the first addressing cycle. Now we're going to access the 4 words in parallel, and the assumption here is that each word is 32-bit, so it's 4 bytes. So it's going to take me 15 cycles to transfer it here, and then 15 cycles to actually wait for the memory, to access the memory, and then 1 bus cycle to transfer it to the cache. So it's going to take me 17 bus cycles to transfer 16 bytes. So the bandwidth is 16 divided by 17 cycles, or 0.94 bytes per cycle. So that would be the miss penalty. Here for interleave, I'm going to have 1 cycle to address, because I can address all of them. But since they are separate memories physically, the access is being done in parallel for all of them. But then it's taking me 4 cycles to transfer each word because I have an error bus. So the miss penalty in this case is 20 bus cycles for 16 bytes. So the bandwidth is 0.8 bytes per cycle. These two and this, so these two approaches are improvements, both of them, over this one. This one, it would take 1 cycle to address it, 15 to get the item, the word, and 1 to deliver it. So it would be 17 per word. So this would be 17 times 4 bus cycles. That would be the miss penalty to transfer the 16 bytes. And this is the best case, which essentially scales down for the miss penalty as wide as you have this bus. So this would be 4 times faster than this, because this bus is 4 times wider than this. But again, and that's the best case that you can have. But we have the issue of the actual real physical issue of a wide bus, and this is the compromise. And it gets pretty close. This would be 17 best case, worst case 4 times 17, so 68, and this is 20 without the problem of the wide bus. So that's pretty good. So that's why we use this. All right, so what else about storage? So we're all familiar with this. We have flash. It's solid state, no mechanical parts, so it is going to be 100 to 1,000 times faster than the disk. It is definitely smaller, lower power, more robust. It's solid state, but it's much more expensive than the disk. Even as inexpensive as it is, and it continues to get less expensive, it is more expensive. But now we have seen, for the last couple of years at least, if not longer, we are seeing that we have solid state drives. Still, it's not where we would like it to be. I mean, 100 gigabytes of solid state drive doesn't do it for me. I need a terabyte. So, well, we'll get there. And I do believe that eventually, at least for things like laptops and actually, any type of personal computer, the disk would be obsolete. The magnetic disk. You'll still have it because we still have to. Data is the consumption and the storage of data is growing at a highly exponential rate. We are, as you know, storing everything about everybody. So we still needs lots of disk. Google and Facebook will need lots of disks, but I believe that pretty soon, probably in the next couple of years, we won't see it in our laptops and any other type of personal device. A little bit more about Flash. There are two architectures when it comes to physical design. One is called NOR, a NOR bit, which resembles a NOR gate at the transistor level. And the good thing about, or a characteristic of this architecture is that you can access randomly the actual bytes. You can read and write actual bytes. So if you are using Flash and like your microcontroller has Flash and it needs to access code a word at a time, then that's what you have in there. You have NOR type, okay? So the other type is NAND. So the bit cell resembles a NAND gate is smaller, but you have to access it a block at a time. You cannot really access it a word or a byte at a time. So you use that for bulk type of storage. So that's what you would use in a solid state disk. That's what you use in your flash drives, USB flash drives, and things like that. It does wear out, so that is actually a real concern, although that type of reliability metric continues to get better as well, but it does wear out. Normally you can read and write. The problem is not so much on the read as it is on the write. But normally the endurance, which is the real name of that metric, the endurance of Flash, is really on the hundreds of thousands of write cycles. And the reason that it does wear off is because you need high voltage to program the Flash or actually write it. Reading it is not an issue. It's more on the writing. It is on the writing. And you have to use high voltage because Flash uses a special transistor, which is a MOSFET with double gate. There is a floating gate between the gate and the channel, and that's where you actually trap the charge. You trap the charge and the electrons in this floating gate. So to get the charge in that floating gate requires high voltage, and that eventually damages the transistor. And how many times you can actually write to the Flash is called the endurance. So some systems do a small smart stuff like leveling the wearing of the Flash bits and moving items and try to, if they detect that a sector or a block of the Flash is being written a lot, maybe after a while they map it to another block that hasn't been written so much. So things like that can be done, certainly on disks, on solid state disks, so that they last longer. And that's why I believe that they're going to replace the magnetic disk on personal devices.